Okay. Can everybody hear me? Okay. My name is Ilya. I'm an organic chemistry tutor. I work with the peer tutoring lab at the basement of the library, and welcome to your first OCHEM 1 exam review session. I hope that the session is helpful for everybody, and before we get started, I just want to talk about two things. I've made a series of questions in the format of a mock exam. I thought it would be more beneficial for you guys to go over some more practice problems rather than me re-lecturing or reteaching stuff that you might already be aware of. I thought it would be better to put them into practice. And lastly, I don't know what your exam looks like. I don't know the format. I don't know what will show, what won't show. These are questions that you're going to have to direct to your professors. Now, any questions before I get started? Okay. So for our first question, we're doing ranking problems. Now, in part A, can everybody see what I'm writing? Okay. So in part A is asking us to rank the following molecules by acidity. 1 is the most acidic, and 5 is going to be the least acidic. So when I'm talking about an acid, I'm talking about a compound that is capable of deprotonating hydrogens and maintaining or gaining electron density. Anything that can do this efficiently is going to end up being a good acid. Now, what contributes to this acidity? Well, first of all, it's going to be resonance. Resonance, whether a compound has resonance, and if 2 or 3 compounds or even all of my compounds have resonance, how many resonance structures they can have. So not only resonance, but the number of resonance structures they can have. Okay? Now, the second factor that's going to be contributing to your acidity is going to be atomic radius. So, what am I saying when I'm saying atomic radius? Essentially, whenever your atom begins to deprotonate, whenever it loses its proton, it's going to gain an electron density, correct? In the form of a negative charge. So when this happens, atomic radius is going to play a very important role. How? Well, whenever I have an atom that is larger in atomic radius compared to an atom that might not be, for example, let's compare nitrogen and phosphor. Phosphor is going to have a larger atomic radius compared to nitrogen, and therefore it's going to have a larger surface area. This larger surface area will help distribute this negative charge around a very large surface compared to a smaller surface. That's why a large atomic radius is going to be good for acidity. Now, my third factor is going to be electronegativity. So I'm going to repeat. An acid wants to gain electron density, wants to gain negative charge. Therefore, if I have an atom that is high in electronegativity, it will be able to handle that gain negative charge much better than something that isn't as electronegative. Okay? And lastly, it's going to be our inductive effects. So when I'm talking about inductive effects, I'm talking about specifically electron withdrawing groups. So my electron withdrawing groups are going to be things like fluorine, chlorine, bromine, things that are really, really electronegative. When I have these close to my conjugate base, or the atom that's carrying the negative charge, it's going to help stabilize this dipole moment that I've generated. Whereas if I have an electron donating group, this is going to be making stuff more basic. Essentially, electron donating groups like methyl and ethyl, let's say, hydrocarbons. These guys are donating electron density onto your already gained negative charge or electron density. This is going to be making stuff more basic, less acidic, or less stable, you could say. Now, with this in mind, let's go ahead and see what we have here. So, first thing I'm looking for, resonance. But before we do that, let's go ahead and deprotonate our most acidic hydrogen and replace them with a negative charge. So the acidic hydrogen is going to be this, over here is going to be this, 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 and this. So can this resonate with anything? This is sp3, this is sp3, 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 sp3. So I'm not going to have any resonance here. What about this guy over here? Again, sp3, sp3, everything is sp3. I cannot resonate with anything here, so this one doesn't have resonance either. And it's going to be the same with this guy. It's essentially the same compound, only with sulfur, so this won't have any resonance either. And it's going to be the same with our last compound. Now what about this guy? So when I'm writing COOH, I'm talking about carboxylic acids. You might get them like, well, COOH, CO2H, or they might just go ahead and draw it out for you. It looks like this. So I'm getting rid of this hydrogen and replacing it with a negative charge. Okay? So what does the resonance look like? Well, I can have this extra lone pair, form a double bond here, break this guy, give the electron to oxygen. So my resonance will look like this. Since this is the only compound that has resonance, and since resonance is the most important factor for determining acidity, this is going to be compound number 1. Okay? Now what about the rest of them? We said they don't have resonance. And since we're comparing oxygen, oxygen, sulfur, oxygen, we can't be comparing electronegativity because, well, we all have oxygen and 1 sulfur. And in your periodic table, you have carbon, nitrogen, oxygen, fluorine, and then you're going to have silicon, phosphorus, sulfur, chlorine. Now these guys are in the same column. So as I go down the periodic table, my atomic radius is going to increase. So I'm talking about atomic radius with these guys. Since I have 3 oxygens and only 1 sulfur, and since sulfur is going to be the one that has the larger atomic radius, this is going to be my second compound in terms of acidity. Any questions so far? Okay. So that's that. But what about the rest of my remaining compounds? If you pay attention, you see that over here I have a fluorine, over here I have no groups, and over here I have an extra methyl. Since I just discussed that inductive effects, specifically electron withdrawing groups, are going to be playing an important role in determining acidity, this is going to be compound 3. All of them have oxygen, none of them have resonance, but this guy has an extra electron withdrawing group, so this is going to be number 3. What about the 2 remaining ones? Well, if you look closely, like I told you, my electron donating groups are going to be hydrocarbons mainly. Methyl groups, ethyl groups, propyl groups, just hydrocarbons. These guys are going to be making stuff basic, not acidic. So, because this guy has an extra methyl group attached to it, it's going to be less acidic compared to my first compound here. Therefore, this should be the least acidic, so number 5, and this should be number 4. Let me just do this. Any questions on part A, question 1? I'm going to get back to you. Go ahead.
Could you explain again why you rank it 4th and 5th?
Of course, of course. So I'm comparing these 2 compounds, right? So like I told you, electron donating groups like methyl and ethyl, hydrocarbons, are going to be making stuff more basic. Remember, bases want to lose electron density. Acids want to gain electron density. So when I'm giving off even more electron density with this guy onto this oxygen, I'm making it more unstable or less acidic. Because this guy doesn't have the methyl group and this guy does, this will be less acidic than my first compound. So this should be 5, this should be 4. Does that make sense?
Yeah.
Okay. You had a question?
You answered it.
Oh, okay, perfect.
You have a question in chat.
Okay, so let's see what our question is. Could you please re-explain why the cyclohexane isn't acid number 2 as opposed to the pentane with sulfur? Oh, because. So according to the trend that I've written here, your atomic radius is going to be more important than your inductive effects. Because between these 2 compounds, remember, I'm comparing atomic radius because, where did I, here. Sulfur is going to be beneath oxygen. And since it's beneath oxygen, if it's 1 or beneath it, it's going to have a larger atomic radius. And because of that, this should be number 2, this should be number 3. Okay? So moving on to part B. So this question is telling us to rank the following conformers by stability, with 1 being most stable and 5 being least stable. Okay. So if you look closely, you'll notice that I'm comparing Newman projections here. So first things first, when I'm talking about Newman projections, I can have two main conformations, either staggered or I can have an eclipsed conformation. Now between these two conformations, which one's going to be more stable, staggered or eclipsed in your opinion? Exactly. Staggered is going to be much more stable compared to an eclipse, because in eclipse you're essentially having this extra torsional strain or the repulsion between the groups on your atoms. So with that in mind, let's go ahead and select our eclipsed one. So it's going to be this guy and it's going to be this guy. So based on the information I gave you, I already know that these two should be 4 and 5. I don't know which one's 4, I don't know which one's 5, but I just know these should be the least stable because they're eclipsed. So I can write E for eclipsed, S for staggered, staggered, staggered. Okay? Go ahead.
What does pH stand for?
pH stands for phenol. It's the same thing as benzene, so it looks like this. Or you could have it look like this. These two are the same thing. Okay? So yeah, this is your pH known as phenol. Good question. So here, let's determine which one's going to be the least stable that I could have. Now over here, as I showed you, phenol, my pH, or benzene over here, has 6 carbons. 6 carbons, and each of them can carry 1 hydrogen. So this is a big compound. And over here, this guy is going to be my T-butyl. This guy looks like this. So if this is my R chain, or the rest of my hydrocarbon chain, this is what CCH3 looks like. C, CH3, CH3, CH3. So this is another really, really bulky group. So when I'm comparing these two guys, over here I can see that the bulkiest group on the front carbon and the bulkiest group on the back carbon are occupying the same exact length. When this happens, you're going to have an extremely high steric strain, which will cause repulsion and therefore increase your energy levels. That's why, compared to this guy, remember, I'm separating these two guys in my eclipse conformation compared to this. These are my bulky groups, and over here they spaced out a little more, but over here they're eclipsing each other. Therefore, this should be your least stable compound, and this should be number 4. Okay? Now, what about the rest of my staggered conformations? So let's take a look. So over here I have methyl and C2H5. This is going to be your ethyl, so it looks like this. If this is my R chain, and CH3 is just going to look like this. Okay. So here I have methyl ethyl, methyl T-butyl phenyl, methyl T-butyl phenyl. So already I know that whatever conformation I'm doing for either one of my Newman projections, this has the less bulkier groups compared to this guy and this guy. Therefore, this should be more stable than all of your compounds. Okay? Any questions so far? Okay. Now, what about these two guys? So here, let's take a look. Over here, I have phenyl and my T-butyl, again, my two bulkiest groups facing exact opposite to each other. So they're an anti-conformation, you could say, my bulkiest group facing away from each other. Well, over here, sure, they are staggered, but they're not anti to each other. They still have the 60-degree angle. So because over here, my phenyl and T-butyl are facing anti to each other compared to this is going to be more stable than this guy. So this should be number 2. This should be number 3. Any questions on part B? Okay. So part C is asking us to rank the following molecules by their boiling points, 1 being the highest boiling point, 5 being the lowest. So take a look at the compounds over here for you. I have hydroxyl, 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 hydroxyl. Now from Gen Chem, you might remember, your boiling point is depending on your intermolecular forces, not as much on your intramolecular forces. So what were your intramolecular? So you had H bonds, then you had your what? Ion dipoles, dipole. What was that? Oh, of course. I'm sorry. There it is. Can you see it now? We're good? Okay, thank you. So we have hydrogen bondings, ion dipole, dipole, and lastly is going to be my dispersion forces. So based on the trend I've written for you, according to this trend, anything that is capable of forming hydrogen bond is going to be much tougher to break compared to, for example, just having dispersion forces. Therefore, if I am capable of forming a high number of my H bonds, or if I even have them present, it's going to be a much larger boiling point compared to something that is only dipole, or dispersion. Now, when am I going to have my hydrogen bonds? You're going to be forming hydrogen bonding when you have your hydrogen attached to fluorine, oxygen, nitrogen, even be close to these guys. Fun. Now over here I have hydrogen and oxygen, and the same thing over here. The only compound that doesn't have any hydroxyl group is this guy. Therefore, immediately I know this should be number 5. All of them have hydroxyls, all of them can form hydrogen bonds, except for this guy. This guy can only form dispersion forces because it's a hydrocarbon. Excuse me. Now what about the rest of my compounds? So over here, I have one hydroxyl, one hydroxyl, one hydroxyl. Here I have 2 hydroxyl groups. So that would mean the frequency of my hydrogen bonding is going to be higher in my first compound compared to the rest of these guys because I have 2 hydrogens on each equivalent of my compound that could hydrogen bond. Therefore, this would be my number 1. And also, I just want to pause here and point something out. If you've been paying attention, you've been noticing that I'm ranking 1, 5, and then keep going to 2, 3, and 4. 1, 5, 2, 3, and 4. I encourage you to do this on your quizzes and exams. It's going to help you rule out 1 and 5 really easily. You know what's most stable, most acidic, most basic, least stable, least acidic, and so on. So I determined 1 and 5. Now what about the rest of these guys? All 3 of them have 1 hydroxyl group, so how do I compare them? Well, let's see. The first thing that's going to pop out to me is going to be this branching over here. So when I'm talking about boiling point specifically, boiling point, not melting point, not just boiling point. Branching is going to be hurting your boiling point. It's going to be decreasing it because boiling point is going to be dealing with high surface areas basically. So when I have branching, this is going to be decreasing my surface area. Therefore, this guy compared to this compound, and this compound is going to have a lower boiling point. Therefore, this should be number 4. Branching helps with melting point. Branching increases melting point because it's helping your compound get packed really tightly, but it's not going to be helping with your boiling point. It helps against it, or works against it, sorry. What about these 2? None of them have branching points. None of them have a spare hydroxyl group. Both of them have 1 alcohol. So how can I compare them? Well, this guy has 1, 2, 3, 4, 5 carbons. This guy has 1, 2, 3 carbons. So both of them can form 1 H bond. However, here I'm talking about dispersion forces now. The intermolecular force that you can have between your hydrocarbons or between non-polar compounds, basically. So here, the rest of the chain is going to be non-polar. Now, when I increase the surface area of my hydrocarbons, or I increase this hydrocarbon chain, this is going to increase bonding and therefore increase boiling points. So I can form the dispersion forces between 5 carbons versus only 3 carbons. So knowing this, I would know that this should be number 2, and this should be number 3. Any questions on part C, boiling points?
There might be an answer in a question, sorry, in chat.
Okay, so let's see. So is the far right more stable because there's a smaller group? Oh, okay. So they had a question on part B. So they're asking, is the far right more stable simply because it has smaller groups? Yes, yes. Because it's staggered and it has smaller groups compared to these guys. These guys have T-butyls, they have phenols. You got 6 carbons over here, 1 hydrogen in each of them. So these two are your bulky guys. This guy doesn't have them. This guy is only dealing with methyl and ethyl correspondingly. Okay, so electron surface area, yes, yes. So alcohols over here, so they're asking, does our hydroxyl group take priority over dispersion forces alone or surface area? Yes, that's true. Because like I wrote here, our trend is H bond is going to be stronger than your dispersion forces. Dispersion forces are talking about surface area. Okay. Okay. So the rest of this page is going to be dealing with this compound specifically. Now, just a side note before I start the question. You might be seeing this guy over here and the same over here. This is supposed to be theta. It's not a negative charge. I've written it here. That's supposed to be theta, like an angle. It's not going to be a negative charge. So, according to this compound, indicate the hybridization of each labeled atom. Well, let's begin with N theta. So over here, my nitrogen, it has 3 bonds, and therefore it won't have any charge, and it's going to have 1 free lone pair. So here's where you're going to have to be asking yourself, is this lone pair going to resonate with anything, or is it just going to be there? So let's take a look. So over here, my benzene ring, it looks like this, right? That's my benzene ring. So when I have this nitrogen over here, I can use this lone pair, form a double bond here, break this guy here, and then have nitrogen here. Oh, and nitrogen had 2 bonds, so over here I'm going to write my 2 bonds. But since nitrogen lost an electron or gave an electron away to form a bond, it's going to be positive. And since this carbon gained an electron, it's going to be negative. So it can resonate with my benzene ring. Now what about this carbon over here, my carbonyl carbon? The same thing is going to be holding true for this one as well. So if I have my nitrogen here attached to my carbonyl carbon, this lone pair can do the same exact thing. It's going to resonate here, form a double bond, and this electron is going to move on to my oxygen. So my resonance structure will look like this. Since nitrogen, again, lost an electron, it becomes positive. And since oxygen is gaining an electron, it's going to become negative. Now, why did I discuss resonance? Because, as you know, your single bonds or sigma bonds are going to be using hybridized orbitals, like sp2 or sp3 or sp, where areas, your double bonds and triple bonds, are using pi bonds which use p orbitals. Therefore, if this lone pair can form a double bond, it has to be in a p orbital. Therefore, the hybridization of this guy is going to be, let's see, 1, 2, 3. It should be sp2. It can't be sp3 because then that would mean I'm not capable of forming a double bond. I just proved that I can form double bonds by resonance here. Therefore, this lone pair cannot be in a hybridized orbital. It has to be in a p orbital. Okay? Now, what about oxygen here? Let's take a look. So oxygen has 2 lone pairs. Okay? And it has 1 double bond. Remember, each single bond, double bond, and triple bond all count as 1 domain. So I'm counting 1, 2, 3. So since I have 3 domains, this should also be sp2. Wait, some of you might be asking, well, didn't you just show that this oxygen can get a negative charge? So it should have 3 lone pairs. So why aren't we doing sp3? The same reasoning I used for determining a hybridization of this nitrogen. Remember, if this lone pair can form a double bond, which can, therefore it cannot be in a hybridized orbital. It has to be in a p orbital. Therefore, that guy is going to be in my p orbital, so I'm not counting that. Instead, I'm going to be counting this lone pair, this guy, and this double bond. So it's going to be sp2. Any questions so far? Okay. Now what about in lambda? So wait, in gamma, sorry, this guy. I apologize. So we're talking about this nitrogen. So we're not talking about CN. What does CN look like? Remember, carbon has 1 bond to the ring, so I'm just going to write R for R chain or ring, whatever you want to call it. And it's attached to nitrogen. Since carbon needs 4 bonds to become octet, I can just make this a triple bond. And nitrogen needs 3 bonds, so everybody's happy and octet. But still, remember, nitrogen has 1 lone pair. So what is going to be the hybridization of this guy? Since this is going to be forming my triple bond, is going to be forming a linear structure like this. So whenever I'm drawing my line angles, remember, I can't just put a triple bond here. It has to be something linear like this, and then continuing my line angle. Okay? Since it's linear, it's going to be 180. And since I have 2 domains, 1 triple bond, remember, my triple bond, double bond, single bonds are counting as 1 domain. So since this is 1 domain, and this is going to be another domain, my lone pair, so I have 2 domains, this is going to be sp. Okay? Now what about carbon theta? So let's see, how many domains does this guy have? It has 1 double bond, it has another single bond, and another single bond to nitrogen. Since that's 3 domains, this guy has to be sp2. And in either conformation of my resonances, it just has 1 double bond remaining. It's not changing anything about it. It's not gaining a charge, it's not gaining a lone pair, it's not doing anything. Okay? Now what about carbon alpha? So I'm talking about this carbon. Well, you might be thinking, hey, can't it resonate with this guy, this oxygen over here? Well, let's see. Remember, in your line angle diagrams, you're not drawing your hydrogens unless they're attached to non-carbon atoms. So here I have 2 hydrogens, okay? Therefore, if I form a double bond here, if I resonate any lone pair here, I have to get rid of one of them, and that will no longer be resonance. Therefore, since I know I can't form any resonance structures, this is 1, this is 2, this is 3, this is 4, so this should be sp3. So this carbon only has 4 single bonds, therefore 4 domains, therefore it has to be sp3. Now what about n lambda? So can this guy resonate? Let's see. So I'm saying I have 2 hydrogens attached to nitrogen, and I have 1 bond to the ring and 1 lone pair remaining. Can I resonate this lone pair over onto the ring? Well, the problem is this guy's sp3, it has 1 hydrogen. This guy's sp3 and it also has 1 hydrogen, therefore, and this guy is sp3 and it has 1 hydrogen. If I put a double bond anywhere there, it's going to be breaking that bond and it's no longer going to be resonance. Therefore, this guy has to have 1, 2, 3, 4 domains and therefore should be sp3. Any questions so far?
There were some questions in chat.
Let's see. So, let's see. So I just explained that, assigning the lone pair to orbitals. Is nitrogen also bonded to the carbon above? Which one? This nitrogen is bonded to this carbon. This nitrogen is bonded to the carbon that's bonded to the ring. And no, it won't get a positive charge. Okay. C from benzene, C triple bond N. Yes, that's correct. C from benzene, C triple bond N. Okay. So what about part B? It says identify 6 different functional groups in this molecule. So before I start answering this question, have you guys gone over functional groups yet? So do you know what amines are? Alkanes, alkenes, alkynes? Okay, all right. So let's see what we have if I start from here. So over here, if I have an S attached to hydrogen over here, it's going to be looking like OH basically. So I'm calling this alcohols, I'm going to be calling these thiols. So whenever I get this sulfur in my compounds, I'm going to be adding this TH over there. Like alcohols, now I'm having thiols. So I'm definitely going to be having the thiol over here with this guy. And over here, I have nitrogen attached to 2 hydrogens and a carbon. So since it doesn't have any pi bonds, this is going to be a simple amine. And over here, remember in the very first question I was talking about this. This is the same as your COOH. It's going to be CO2H. This is going to be your carboxylic acid. It's the same one I was talking about in the very first question that we saw. So this is
Hey, we can't see the bottom, by the way.
Carboxylic acid. Now over here, if I have a carbon that's triple bonded to nitrogen, this is going to be your cyanides or nitro groups. Either one is fine. Now here, if I have carbon, go ahead. Excuse me, I can't hear. Of course, of course. Okay. So I'm going to have nitro for C triple bond N over here. This is going to be nitro or cyanide, whichever one you want to call it. And over here, if I have carbon-carbon double bond, this is what you know as your alkenes. Now what about this oxygen over here? If I have an oxygen in between my hydrocarbon chain, not at the end, not terminal oxygens, if I have it in between them, like this is going to be counting as an ether. Okay? Now that's 6. If I wanted to name this, well, if you have a carbon double bonded to oxygen, which is also attached to a nitrogen, this is what you will know as your amide. So that's all. Now what about part C? So it's saying what is the bond angle between N theta's lone pair, and C theta. So I'm asking about this lone pair, nitrogen, and this carbon specifically. So my question to you, did this nitrogen resonate? Did it form resonance structures? Yes. So since it did, that would mean that this lone pair has to be in a p orbital. And if you remember from Gen Chem again, your sigma bonds are head-to-head bonds that look like this. Head-to-head bonds. Whereas your double bonds and triple bonds are going to be your p orbitals that are parallel to each other that look like this. They're not head-to-head. Now, if I were to draw this structure three-dimensionally, since that lone pair is in the p orbital, it has to be directly perpendicular to the surface. So, for example, I will have my sp2 here, sp2 here, sp2 here. This p orbital will be directly perpendicular to the surface. Okay? Therefore, if it's perpendicular to my surface, it should be 90 degrees. Okay? Now, part D is saying let's consider N theta and N lambda. So I have this nitrogen and this nitrogen. So it's saying identify the most basic and least basic nitrogen. Okay, again, I'm going to ask the same question. Did this nitrogen resonate? What about this nitrogen? Did this nitrogen resonate? Exactly. Now, when I'm talking about basicity, not acids, bases. Bases are all about giving electron density away. They're all about donating electron density. They want to get rid of that lone pair as fast as possible. They can handle electron density. So, with that in mind, if this lone pair is resonating and forming a double bond, it's going to be kept in your system. It won't be available for donating it away or kicking it out, reacting with anything. It's too busy resonating, forming double bonds back and forth, back and forth. But this guy, since this guy is not forming any double bonds, any pi bonds, nothing, it's just laying there in the sp3 hybridized orbital, it's much more reactive and ready to just be kicked out. So this guy will be more basic. Therefore, N lambda is more basic. Any question about the explanation?
If somebody doesn't understand the bond angle,
Which one? Bond angle. Oh yeah, the 90 degrees. Okay, sure. So the question was asking about n theta's lone pair, and c theta. So I'm looking at this segment. Okay. So when I'm looking at this segment over here, I showed you that this lone pair is going to be forming resonance. Okay, it's going to be forming a double bond essentially. And from here, I showed you that your double bonds look something like this. They're going to be parallel to each other. They're not going to be head-to-head. They're going to be parallel. Therefore, if I'm forming double bonds between this guy, the lone pair that's here, and here with my carbon, that lone pair has to be in a p orbital, and therefore it's going to be perpendicular to my surface. Okay? So since it's perpendicular to the surface, it has to be 90 degrees. Any questions on this entire question I did? Part A, B, C, D, anything? For D, yes. D was N lambda is going to be more basic. Least basic. Oh, so we were comparing just two nitrogens, basically. Yeah, I was asking between two nitrogens. I was essentially saying, so this was supposed to be three nitrogens, but I saw this guy and said, well, it would be unfair to ask you guys to determine basicity between this guy and this guy. So I just erased this one and said, well, between these two nitrogen, which one should be more basic? That's all. Questions?
in chat,
I'll answer.
So there's no way to determine I guess, the order for the three?
You can determine it if you want. I can explain it. I was just saying, well, think about it like this. So like I told you, my bases are all about donating electron density, okay? They're all about giving electrons away. Now, from this question, I determined that this nitrogen's hybridization, what was it, N-gamma, is going to be sp, okay? So this lone pair is going to be in my sp orbital. This lone pair, from what I determined, my N lambda, is going to be in the sp3 orbital. And this one is going to be resonating. Now, let's compare these two specifically, since you asked about these. So this guy is sp3, this guy is sp. Do you remember things such as S character, P character from Gen Chem? If not, I can refresh it. So think about it like this. When I'm talking about S character, essentially your p orbitals and s orbitals are going to be intermixing with each other, right? They're going to be mixing up to create a hybridized orbital. So when I get that, let's say I have sp3. So I would have 3 p orbitals and 1 s orbital. So that one orbital is going to have one for 25%. So your hybridized orbital is going to have 25% s character. Now what about sp? I only have 1 s and 1 p. So this is going to be 50% s character. Now why am I talking about s character specifically? Because in your orbital energy diagrams, you had S over here and you had P over here, and in between them you would have your F and D. But here I'm talking about these two. Because the energy of your P orbitals is going to be higher than your S orbitals, having your lone pairs in these two will determine reactivity. So if I have my lone pair in my S orbitals, it's going to be much more stable, less reactive. But if I have it in my P orbital, or if I have more P character in my hybridized orbitals, it's going to be less stable and therefore more likely to react. What? Okay. Liz, you said we had a question online?
yeah, there's a couple.
Okay, so let's see. Okay. How do you determine which orbital the electron is in? Well, that will depend on if you're forming resonance or not. For example, here, this guy was forming resonance, therefore it had to be in a p orbital. Because if I'm forming double bonds are going to be p orbitals or pi bonds over here, Arvin. So double bonds and triple bonds are going to be using pi bonds, which are using p orbitals correspondingly. Okay. Oh yeah, I explained that. Okay, all right. No, the answer to the question themselves. Yeah. Okay. Any questions on this page before I move on? All right. So, nomenclature. I don't think you guys like this part a lot. So, when I'm talking about nomenclature, well, right now you've learned about nomenclature of alkanes so far. You haven't discussed alkenes or alcohols or ethers and so on, so I'm just going to worry about this. Now, when I'm talking about nomenclature of alkanes, the first step to determining it is going to be, first, my longest chain. So how many carbons will be in my chain? Let's see. If I go this way, I'll have 1, 2, 3, 4, 5, 6, 7. If I go this way, I'll have 1, 2, 3, 4, 5, 6, 7, 8. Therefore, I already know this should be my main chain. So whatever I have, since it has 8 carbons in it, it's going to have octane at the end. Okay? Since I'm having 8 carbons in my main chain, I'm going to be having octane, ane for alkanes. So that aside, how do I go about numbering this? Well, let's take a look. If I number here, I'm going to have 1, 2, 3, 4 fluorine, 5 methyl, 7 chloro. But if I start numbering this way, I'm going to have 2 chloro, 4 methyl, and 5 fluoro. So if you pay attention, I have my lower numbers if I count from the left. And that's my goal in determining nomenclature. I want to have the lowest numbers assigned to my substituents. I don't want to have 4, 5, 7. I want to have 2, 4, 5 instead. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now this is numbering. So what about the name itself? Here I'm going to work alphabetically. So chloro is going to be coming first. So I will have 2 chloro. And remember, I'm putting dashes in between everything I write. You're only going to have commas when you have your substituents on the same exact thing, or they're the same substituents. I'm going to explain it later on in this example. Okay, now what about the rest of them? So I have methyl, I have ethyl, and I have fluoro. So E is going to be next. So what are we going to have? Since this is on the 5th carbon, it's going to be 5 ethyl. And what about the rest of them? F comes before them, so I'm going to have 5 fluoro, and you don't have to make them capital. You can just write them normally. So what am I left with? I'm left with 2 methyl groups. So this is going to be on my 1, 2, 3, 4th carbon. So I'm going to have, this is when I use my commas, 4 and 4 dimethyl. And then at the end, you're going to have your carbons. So it's going to be octane. Yes, go ahead.
Why do you dimethyl and then ethyl?
Because, oh, you're asking, well, since, oh, okay. So why this before my ethyl, right? It's alphabetical. If you notice, I've been saying C, E, F, M. D over here is not going to be alphabetical. Di, tri, tetra, mono, these are not going to be alphabetical. The only time when something like this matters alphabetically is when you have iso something, like isopropyl, isobutyl, then that matters. then you're not going to say, oh, it says isobutyl, then B comes before this, it has to be in the beginning. No, 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 no. You have iso. This is the only time alphabetical is going to matter. Any other questions?
Wait, so not T-butyl, like the T doesn't count?
Not T-butyl, not N-butyl, not sec-butyl, just iso. Okay. So let's move here. Since we have a cyclic compound over here, and it's going to be my highest number of carbons, whatever I have at the end is going to have cyclo. And let's see how many carbons are in here. 1, 2, 3, 4, 5, 6, 7. So cycloheptane. Whatever I have in the end is going to have cycloheptane at the end. 7 carbons, cyclic, cycloheptane. So let's go ahead and start numbering. Well, here you might ask, well, how do I start numbering? Should I say 1, 2, 3, 4, or should I say 1, 2, 3, 4, 5, and then 6? How should I number this? Well, again, same rule applies. You want to have the lowest numbers assigned to your substituents, lowest numbers. So if I start here, I'm going to have a lower number on this guy. If I start, for example, from here, I'm going to have 1, 2, 3, 4, 5, 6. Here I'm going to have 1, 2, 3, 4 over here. Therefore, my numbering should be 1, 2, 3, 4, 5, 6, and 7. Go ahead.
Could you not go like counterclockwise, or do you always have to go clockwise with
Counterclockwise. So if I go this way, right, I will have to start from this guy, right? Since this will be 1 and 2. Remember, I want to have the lowest quantities I'm not available. So, for example, I want this to be on 1, for example, instead of 7.
why couldn't you start from like where the 4 is right now?
So I would go 1, 2, 3, 4, and I would go 1, 2, 3, 4. So here I have 2 substituents on the lowest numbers compared to just 1. So I have 1 and 2 instead of 3 and 4.
Oh.
Okay? Does it make more sense?
Yeah.
Okay? Good question. So over here, I'm going to have bromine come first alphabetically. So we're going to have 1 bromo. Okay? And then here, you might have been looking at this guy and say, well, how the heck do you name this guy? The thing is, this is going to be your complex group. This is going to be forming your complex group. So once I say 1 bromo and then 2 ethyl, what carbon is this on 4? Here's where I'm going to be opening a parenthesis here to name this separately. So when you're naming complex groups, remember, the first carbon that is attached to my main ring or my main hydrocarbon chain is going to be carbon 1. So this is carbon 1 or C1. From here, you're going to do the same exact thing you've been doing so far. Just find the longest hydrocarbon chain that you have. So I have 1, 2, 3, 4, 5. So whatever I have is going to have pent at the end. Well, remember, because this isn't my main chain is my cycloheptane, this is going to be counted as a substituent. So it's not going to be pentane, it's going to be pentyl. Remember, this YL has been used for anything that has been a substituent so far, and it has been a hydrocarbon. For example, ethyl, methyl, propyl. And this one's going to be pentyl. So name this just like you would name any regular hydrocarbon. So the first carbon has what? 1, 2 carbons, so this should be ethyl. So this should be 1 ethyl. And then the rest of them. How many carbons do we have? 1, 2, 3, 4, 5. So this should be pentyl. That's it. You're done with your complex group. So just close the parentheses. And then, what is my main hydrocarbon chain? It's going to be cycloheptane. So I'll have this dash between here because I really don't want to write it again. So we're going to have cycloheptane. Good. So, all right. Any questions so far? Go ahead.
How do you need to do the complex group thing?
Oh, Well, so far you've been taught about isomers of propyl and butyl, I'm assuming, right? N-butyl, sec-butyl, isobutyl, if I'm not mistaken. I don't think they've asked you to know things that have 5 carbons. Okay, so I'm assuming, I would appreciate if you ask your professor, you've been taught to know 4 carbons as substituents, like butyl, or sec-butyl, isobutyl, or propyl for 3 carbons. So this guy is 5 carbons, and in addition to that, it has 2 carbons over here. Okay. But if you feel unsure about naming a compound, for example, you see T-butyl, you don't remember it, you're fine to just use this. It's okay if you use this. You could do like, I don't know, 2,2-methyl, 2 and 2-dimethyl ethyl, basically. That's fine if you do that, if you don't remember it. Any other questions? Go ahead.
Could you explain like the dashes inside the parentheses and outside, like the ethyl butyl?
Oh yeah, so this is a big dash as well. I just want to point that out. I just didn't want to rewrite this, that's all. Okay? So remember, the only time I'm using commas is basically if I have the same substituent like methyl, let's say, or ethyl, repeating in my hydrocarbon chain. So that's when I use, for example, 4. For example, 4 and 4 and 5 trimethyl something. But other than that, I'm putting dashes in between everything. And here you might be asking, well, why didn't I put a dash here? It's okay if you do. There's nothing against it. For the last thing, when you're trying to connect it to your main hydrocarbon chain, it's okay if you do put a dash or if you decide not to put a dash. But for the rest of them, you have to put a dash. Okay? Of course, go ahead.
A dash between a 4 and a parentheses?
Yes, you're right. Thank you, catching. Yeah. You're right, yeah.
You said you use commas when you have multiple substituents in the same place.
Yes.
Dimethyl, not just one thing. Why do you do 4 comma?
So you're asking about this one. So I'm saying 4 and 4. Let's say this methyl was on the 6th carbon. I will say 4 and 6, basically. If I have the same substituent repeating, I'm using commas. Does that answer your question, or am I? Okay. Go ahead.
So if both of the methyls run like 3 and 4,
Mhm.
3, 4 dash dimethyl.
Correct. Yeah, that's correct. If I had it on 3 and then 4, it would be 3, 4 dash dimethyl, whatever I have left. Any more questions?
Or some in chat if you're interested.
Let's see. So let's see. They're discussing stuff. I don't think they're asking anything.
We could be discussing, but I think Tariq maybe started with Tariq.
Yeah. No, they're discussing things. They're not asking anything.
Okay.
Yeah. Okay. Thank you, Liz. So let's see. So you might be asking, well, how do I name chair configurations? Well, don't be intimidated by this guy. You can always and always just convert this into a 2D structure. You don't have to do this 3D. But what matters is knowing the stereochemistry of what you're going to get on your resulting 2D shape. For example, if I have something pointing upwards, it's going to be a wedge on my 2D shape. If I have something that's pointing downwards, like an equatorial down or an axial down, it's going to be a dash. Okay? So if I wanted to convert this into a 2D structure, I will have my regular cyclohexane. And then you're welcome to choose any carbon that you want as long as you do 2 things. Number 1, know that these 2 carbons are adjacent to each other. So I can't choose this carbon and then choose this carbon or this one. They have to be close to one another, just 1 carbon away. And 2, you have to indicate your stereochemistry. So for example, if it's going up, it's on a wedge. If it's going down, it's on a dash. So for example, here, this T-butyl group is going to be pointing upwards. Therefore, I have to have it on a wedge. Remember, your T-butyl looks like a fork. And here, since this ethyl group is going to be pointing downward equatorial, I have to put it on a dash. like this. So when I get this, all I can do is, since I have two substituents specifically, I don't have anything else, I could just make it easy and say trans, and then name the rest of my compound. Remember, in your nomenclature, you're indicating your stereochemistry first. Just get rid of it at the beginning and then name the rest of your compound. So for example, if you have R and S, if you have E and Z and so on, indicate that in the very beginning and then start naming your compound. So here I just said trans to say these two are pointing in opposite directions. Okay? If both were on a dash or if both were on a wedge, then they will be cis. So I have trans, and then let's see. So I have a T-butyl and I have an ethyl group. Here you can go either 1, 2, and then the rest of your chain, or you can go 1, 2. Whenever you face this situation, let's say I have two substituents, I can name them either way, and they have the same value, basically. Both of them are alkenes, right? When you get this, just think about numbering based on alphabetical order. For example, here I have T, bu, so since B comes before ethyl, I'm going to name this as 1. Okay, so I'm going to have this B1, this B2. So I'm going to say 1 T butyl, 2 ethyl, cyclohexane. This dash can also not be here, so it's up to you. Okay. So you're asking, what would it mean when there is one S, 2 R at the beginning of a name, and how would you determine it? So the example that I'm doing next, this guy is going to be using the same exact configuration that you're discussing. So I'm going to talk about this right now. Any questions on this before I move on? Go ahead.
Do you have to convert it to a 2D structure as long as you know that if it's playing up?
You don't have to. It's not obligatory. I just did it to make it easier for you guys. You can name it just as it is. You can make it 2D and then name it. It's all up to you. Okay. As long as you know these two are pointing in opposite directions and they're trans. Okay. Any other questions? Go ahead.
Would it be wrong to say 2 T-butyl, 1 ethyl?
So like I told you, this is a question, I remember I asked this in my course too. My professor told me to go alphabetically, basically, if you face this kind of situation. Since both are alkanes, right? This isn't, for example, an amine or a nitrile or a carboxylic acid. If you had that, that would be higher in priority. But since you don't, basically they're the same alkanes, just use alphabetical order to determine number, okay? Because then you start 1 T-butyl instead of 2 and then 1. Go ahead.
Why is it T-butyl and not iso?
So these are all different isomers of the same compound. So butyl means I have 4 carbons in my substituent, okay? So for example, I could have N-butyl. So if this is my hydrocarbon chain, I'll have 1, 2, 3, 4 carbons attached to this. I could have sec-butyl. Again, R chain, 1, 2, 3. This time I move this here. I could have isobutyl, which would be my R chain, 1, 2, 3 over here. Remember, whenever I have iso, I'm basically having a double branching at the end, something that looks like a peace sign. So isopropyl would have a double branching at the end. Isopentyl, iso, I don't know, hexyl or anything. When I'm saying iso, I'm talking about this double branching at the very end. Okay? And lastly, I could have T-butyl. So I have R. These are all constitutional isomers because I'm moving bonds around. If you want to write it down, if you want to take a picture or anything, go ahead. So we have a question saying, what if T-butyl and ethyl switched positions but still pointed in opposite directions? It would still have the same name, so how would we differentiate? So yeah, it would be the same thing. It would be the same exact thing. Because essentially I can just flip my compound and a wedge will become a dash and a dash will become a wedge. Now for the next questions, not this page, the last page that we're going to do, we're going to be talking about isomers over there. That's when I intend to help you guys determine how something is identical, or diastereomer, or enantiomer, and so on. Okay. Any questions on this before I move on? Okay. So what about naming these guys? So when I'm naming Fischer projections, remember, Fischer projection is indicating to you something very important, stereochemistry. So the two ends of my chain in a Fischer projection should be facing away from me, so on a dash. So this is on a dash and this is on a dash. And the rest of my substituents, anything that's on a horizontal line is going to be on a wedge. So these guys look like this. Okay? So when I get something like this, when I'm giving you stereochemistry, I'm hinting to you guys that you have to determine stereochemistry. There's a probability that we have chiral centers here. So let's see. Would this carbon be chiral? Well, this carbon is attached to one chlorine, one hydrogen, one ethyl, and the rest of your hydrocarbon chain with the bromine. So since it is attached to four things, and all four of those things are different, this guy is going to be chiral. Remember, chiral means you have an atom at the center that is attached to four things, and all four things are different with one another. Okay? What about this guy? What about this guy? So let's see. So I have bromine, I have hydrogen, I have methyl, and I have the rest of my chain. Four different things. So this should also be chiral. I don't understand the definition of trans. So trans would mean if I have two substituents that are pointing in opposite directions, basically. So for example, here, since I had one on a dash, one on a wedge, these guys are trans. The same would hold true if I had, let's say, an alkene with your highest priority pointing up and the other pointing in the opposite direction. This is trans as well, this is trans as well. Okay? So back to our question. So I determined this is chiral and this is chiral. Since both of them are chiral, I have to determine stereochemistry. So I would have my highest priority group be number 1, and the least prioritized group going to be number 4. When you're assigning priority in chirality or determining chirality, you're going by atomic weight. For example, I have carbon here, I have chlorine here, carbon here, hydrogen here, so this guy should be number 1. Because I go carbon, nitrogen, oxygen, fluorine, and then here I have chlorine. So this is going to be the heaviest. Therefore, this should be number 1. And whenever you have hydrogen, that's going to be your least prioritized group. So this should be number 4. So how do I determine between my ethyl group, C2H5, and the rest of my chain? Which one should be number 2? Here's the thing. Whenever you have the same atoms attached to your chiral center, whenever this happens, look at what else is attached to that atom. For example, this carbon is attached to another carbon, like this guy, but the rest of my atoms are going to be hydrogen. Here I have one hydrogen and one bromine. Since I have a bromine on this carbon, this is going to be a higher priority. So the rest of my hydrocarbon chain is going to be 2, and my ethyl group is going to be number 3. So let's see. I have 1, 2, 3. So since I'm going counterclockwise, you might say it's this. But here's the thing. In determining RNS configuration, always remember this. Please, please don't make this mistake. Your least prioritized group should be facing away from you when you're determining it. Since this hydrogen is on a wedge, I have to make this the opposite of what it is. So I determined it was S, now it has to be R. Please remember this. Your least prioritized group has to be facing away from you when you're determining S and R. Okay? Now what about this guy? So I know bromine is going to be number 1 since I have carbon, carbon, hydrogen. So bromine is going to be even heavier than chlorine, so this should be number 1. Hydrogen is still going to be number 4. Hydrogen will always be number 4. What about this part? I have a carbon attached to chlorine. I have a carbon attached to 3 hydrogens. Therefore, this will again be number 2. This will be number 3. So since I'm going 1, 2, 3, I'm going in a counterclockwise. You might say it's S. But because this hydrogen is on a wedge, it has to become R. Good, thank you. Any questions so far about determining chirality? Okay. So I determine chirality. Let's see. Let's name this just as you would naming a normal compound. We determine our longest chain first. So over here, if this is my main chain, Fischer projections show you your main chain. Your vertical line is showing you your main chain, basically. So I'm having 1, 2, 3, 4, and 5. Therefore, whatever I have is going to have pentane at the end. Okay. Now, how would I go about naming this? If I started numbering this way, I would have 1, 2, and then 3 chloro something. But here I have 1, 2 bromo. Therefore, I should be numbering this way. And also, there's nothing wrong with converting this into line angle if you wanted to, if that helped you out more. But you can do your nomenclature here as well if you don't want to convert it. So here I have number 2 for bromine. Now I determined both of them were R, so just like our previous example, we determined stereochemistry first and then moved on to naming. So here I'm going to have 2 R, and then this one. This is the 3rd carbon, right? We determined it was R, so this one's going to be 3 R, and then you're free to name your compound, just like you would in a normal situation. So I have 2 bromo, 3 chloro. What did I have? Pentane. Because I have a 5-carbon hydrocarbon chain. So I can see some tired faces. Would you guys like to take a 5-minute break, maybe refresh, grab some water, use the restroom? You look tired, really. Grab some water though. If you get dehydrated, you get tired very fast.
I just have a question. For the chirality, I mean, I understand how it works, but when do we give, do we only give it a given like direction?
Great question. Great question. So remember, I'm giving you a wedge dash direction. I'm generally hinting towards chirality. Okay, but nevertheless, you can also tell chirality is something that, well, you have a chiral system using its forces. So for example, if I have carbon, 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 carbon like this, all of them have 2 hydrogens. That's the same thing chirality doesn't have.
Okay. So if I can identify a chiral atom, I should divide it, right?
Yes, definitely do, especially when I'm giving you Fischer Projection. However, there's something else. I could have just said hydrogen, hydrogen. Then none of them will be carbon. So be sharp.
And then just like this exam, is that something you should always pay attention to? I mean, would that only apply to like chair projections or would that?
You could have chair or you could have alkanes. You could have done ROS for this one as well if you wanted.
But it wouldn't be required, so it's not gonna like clarify what.
It would have been fine if you said ROS, okay? But remember, for alkenes, I like to say ENZ instead of cis and trans when I have two things, because that's more proper. Well, here, I thought trans would make it easier instead of determining is this R, is this S, and then 2R, 2S. I just said trans.
So, I mean, it's kind of like if it's one's R and one is S, that means, or is that? Because.
Not necessarily.
No.
Determine on their highest priority.
That's based on my side. Also, I don't understand why, if they're both next to each other and they're going in opposite directions, one is going to be the same thing, because isn't it kind of like alternate?
Good question. So my tutorial position goes up, down, up, down, up, down, up, down, up, down. My tutorial is pointing up. That's like the tutorial has to be back. So since that one is down, this one's up, they're facing opposite directions. So it has to be right. This is one of the same direction, either it's up or down.
Oh, okay, so even though they're at different positions, like even though they're next to each other, because one's down and one's up, they're still there.
Exactly. Sister trans is indicating opposite or the same direction.
Okay.
So I was talking about nomenclature over here. So just like any normal alkane, you determine your non hydrocarbon chambers, right? So I said over here I have 1, 2, 3, 4, 5 carbons, right? So it should be now I'm talking about where should I put my number? Should I say 1, 2, 3, 5, 6, 7, 1, 2, 3? Let's say I'm low enough. I start numbering. That's what this is. These two are my spiral axes. That's why I put more S for my two axes. These are my axes.
Like, same thing with the axle, right? One goes down, the other one goes up.
For this one, so this is alkane, because this isn't just a cyclohexane with 1 or 2 double bonds. This one, that's a carbon oxygen double bond. You can, whenever you see a double bond, you can't necessarily say, oh, alkane. No, this is one with carbon oxygen double bond and carbon compound. You're welcome. You have the choice of my RNS, but I mean, which one is easier?
And then, can you have like R slash pro dash R
The nomenclature of types have all like this. This way, you're getting rid of the stereochemistry at the beginning, so you don't have to worry about it in between.
No, so. No, I still don't know what body.
This question, I asked the same question for my case. Whenever you're facing the situation when you have substitutions with the same value, you could just say alphabetically, it doesn't matter. For example, I don't have 2 and then 1. I have 1 and then 3. Okay? Does that make sense?
You know what? Most people I know
So for my answer, he looks like. So this one should be 4, 3,
like the other
2.
side.
So this one's COH. So COH. It can be given to a Chirality. This can, since resonance is the first thing that matters, the most important thing, that's going to be number
I mean, this one's like.
Sorry, so I have a question and go out.
Big algorithms, where like if you're silence, I think I could see.
Okay. May I ask a favor? So how long can you stay after?
Oh, I have time.
Okay,
Yeah.
okay. Because right now, since I think we have the room till, I don't know, 4:30, I want to go over the rest of the questions. I promise I'll answer your questions after that. Okay. Okay. So, question 4. We're almost there. So question 4 has given us a structure and it has numbered my hydrogens, 1, 2, 3. So why? Part A is asking me to indicate the most acidic hydrogen between H1, H2, and H3. So we solved an acidity question before, and the same exact factors will be taken into account when we're determining acidity. Again, whichever one has resonance is going to be most acidic, or whichever one is on the largest atomic radius, or most electronegative. But the first one is this. Okay? So let's go from here. If I take this hydrogen off and replace it with a negative charge, this is next to a carbon that has 2 hydrogens, and therefore it is sp3. So because of this, if I put a double bond here, I'll have to be getting rid of one of my hydrogens, so this guy does not have any resonance. What about this one? Well, you might say, hey, this guy's next to a double bond. Can't this resonate here? The problem is, this carbon isn't. This carbon has a hydrogen over there. If I put a double bond there, I wouldn't be able to resonate. So, what about hydrogen number 2? Well, the good thing is, I can put this lone pair here and put this guy here, so I would have a negative charge here and a double bond this way. Because I can do that, and because this hydrogen specifically has resonance, so hydrogen 2 should be most acidic. Okay? So part B is telling me to draw the structure of the conjugate base obtained after deprotonation of the most acidic hydrogen. It's basically telling you what will it look like if I take that hydrogen off. So I already drew for you, but I'll do it again just to. So everything looks the same. However, I just took one hydrogen off. That's all. Now the next question is asking to draw the relevant resonance structures of the conjugate base. So just like I told you, the only resonance structure that I could have would be, oh, by the way, if I'm putting a circle here, this just means there are 3 bonds here. I'm just too lazy to draw them. So my oxygen made a double bond here, gave this lone pair this way to make a double bond, therefore my double bond is here, and my negative charge would be here. That's all. Oops. I can't resonate any further because this guy and this guy, they're both sp3. So that's it. Any questions so far? Okay, I'll repeat. So I'm saying, because this oxygen, so when I deprotonated this, I got a negative charge here, right? So because this lone pair can be given to this location to form a double bond, I can only resonate with this carbon. This one has 2 hydrogens, and this one has 2 chlorines. Since both of them are sp3 and both of them are bonded to something, if I were to put a double bond here, I would have to break one of them off. If that happens, that is no longer going to be resonance. Now, okay. So the next question is asking me to circle the major contributor of the resonance height. So I have this guy, and I also have this guy. So what is the difference between these two? If I ignore the rest of my chain and just look at this segment, solely this part, you would see that my negative charge here is on oxygen versus my negative charge being on carbon. So in your opinion, which one can handle a negative charge better, carbon or oxygen? Oxygen, exactly, because oxygen is more electronegative. Therefore, this should be my major contributor. This one. Any questions on question 4? Go ahead. That is exactly what it means. Major contributor means the most stable resonance structure. Or in other words, since it's most stable, where it's going to be spending the majority of its time. Okay? So here, it's asking us to draw the resonance structures and then circle the major contributor. So here I can go either way. Either I can go this way with this double bond and this charge, or I can go this way. Well, I like to go this way. So let's redraw this guy. So I can have this negative charge go here, form a double bond here, and this electron given to this carbon. So I form a bond here, I break a bond here. Okay? Where can I go from here? So let's say double bond stays. Since I already did this location, then let's play with the upper segment of my compound, this part. So what will this look like? Let's say, well, this carbon has extra electrons and this oxygen is missing electrons, then why else would it have a positive charge? Why not just form a bond with this oxygen? So this way, oxygen can break this bond off and give the electrons to this carbon. So since carbon is getting an electron, it's going to be getting a negative charge. And since this carbon is giving its electron away, it's going to become neutral. Okay? So what else can I do from here? Let's redraw it again. If the upper segment stays where it is, how can I get rid of this charge? Let's see. So I was thinking, why not? Let's see what it is here. Okay. Why not form a bond with this? So carbon has an extra electron again. Why not put a double bond here, break this bond, and give this electron to this carbon? Since this carbon is getting an electron, is going to have a negative charge. And since this carbon is giving an electron away, it's going to become neutral and form a double bond here. Okay? But I'm not done yet. I think this is the last one. So what else can I do? During my entire structures, I've had oxygen with a positive charge. Let's give this electron back to oxygen. What how? This carbon has an extra electron, so why not give this to this carbon, and this carbon gives this electron to this oxygen. So I form a bond here, and since this oxygen no longer has a bond and instead got an electron, it's going to be neutral. Any questions on how I got to this point? Go ahead.
Is the oxygen positive that holds on?
Yes, we started out with oxygen being positive.
Yeah. Right.
Yeah.
But we added.
Oh, I see. Well, forgive me. So the packet you got has a methyl at the end and oxygen doesn't have a charge, right? Yeah, because they changed the questions right before I started them. So I think someone is asking the same question online. I changed this question because that way you will be getting a lot more resonance structures. So I just wanted to change the question a little bit. So yeah, I'm going to scan these and upload these online for you guys, okay? I just changed a couple of things. Go ahead.
The third resonance structure, since you're adding a bond. Oh, no.
You good? Well, yeah, I changed, I think, 3 of the questions a little bit. So if they're a little different, I apologize, but I'm going to fix it and upload it for you guys online alongside the key. Okay? So that's as far as I can go. Now, between all of these structures that I have, which one do you think is going to be the major contributor? Exactly, it's going to be the last one. But why? Why is it the last one? Why isn't it the, I don't know, third one? Exactly. We want to have, even though my entire structure is neutral, remember, all of them have one positive, one negative. They're all neutral. However, I want to minimize charge. And the only one that offers me that option is this guy. Therefore, this has to be my major contributor. Okay? Any questions? Go ahead.
If they're like a math formula or anything we can use to like figure out how many resonance structures we're supposed to have.
You're going to have to draw them out. Yeah, you're going to have to draw them out. Go ahead.
Couldn't you have another resonance structure with 2 double bonds?
See, that's the problem. If you do that, you're making oxygen positive too, essentially, since you have 2 bonds here. So if you have oxygen with 2 bonds, 2 additional bonds, like this, it's going to start looking like carbon. Oh, sorry, I apologize. So if I have oxygen here, originally it has 2 bonds, right? So, yeah, since it has 6 valence electrons. If I give it 2 bonds, that would mean it has to lose 2 electrons. Now, in my periodic table, I have carbon, nitrogen, oxygen, fluorine. If I lose 2 electrons, I'm going to become like carbon. Carbon can form 4 bonds, so oxygen has to form 4 bonds. Now, here's the problem. You're adding a positive 2 charge on your oxygen. That's going to be extremely unstable. You do not want to do that at all. So based on the most stable ones that I've drawn for you, these will be your best options to write down. You do not want to go with a positive 2 charge oxygen. Okay. Any questions? Okay. What?
When you have the double bond, do you have to always turn it into a lone pair, or can you just move the double bond?
I'm not sure I'm understanding what you mean. Do you want to show me something, maybe what you mean?
Yeah, so you know how like you went from the double bond and then you turn it into a lone pair,
Mm-hmm.
and then you turn the lone pair into a bond again?
Yes.
We're not allowed to just move the bond.
To, for example, just put this here and let the charge stay here.
Yeah.
Well, see, the thing is your resonance is all about this road of electron movement, essentially. One thing has to happen for the other to continue behind it. For example, I broke this bond off because I moved this here. Okay? I didn't just move this here and then let this charge stay here. Okay? Questions? Okay. Chirality conformations. So question 6 is all going to be about Chirality conformations. It's asking us, answer the following questions regarding Chirality conformation. So let's draw the most stable conformation of each compound. Now, if you pay attention on all 3 of your compounds, your substituents are repeating. The only thing different about them is whether they're on a wedge or on a dash. Okay? Now, whenever I'm asking you to draw out the most stable Chirality conformation, I want you to remember, prioritize putting the bulkiest group on the equatorial position, okay? Always. So for example, on all 3 of them, the bulkiest group is going to be isopropyl. I know it's iso because, again, it has that double branching at the very end. And since it has 3 carbons, then propyl, so isopropyl. Since this guy is the bulkiest, I want to prioritize putting this in the equatorial position. Because if I put it in the axial position, I'm going to increase my dihedral or diaxial interaction, and that would make my ring very unstable. So whatever I draw, I'm going to prioritize putting that on the equatorial position. Now remember, when I'm trying to convert between my Chirality conformation and my 2D cyclohexane, you have to just obey 2 rules. Number 1, how many carbons each substituent is away from each other. For example, if I choose this carbon, my next carbon can't be this one. It has to be this one or this one. Either this or this. They have to be 2 carbons away. And number 2, you have to indicate your wedge and dash with equatorial up or axial up, equatorial down, axial down. What I'm trying to say is wedge and dash should be indicated as up or down. Okay? So, for example, I told you to prioritize putting this on equatorial. So now I'm going to choose a carbon that allows me to have an equatorial pointing up because this is on a wedge. Wedge means coming towards me. So let's choose this guy. So the next one has to be 2 carbons away. This guy and this guy. If I'm drawing out my ethyl group, since it's on a wedge, that means it's coming towards me. Therefore, it should be on an equatorial going up. Because this carbon, if I want to put something up on this carbon, it can only take equatorial. Axial will be down. And then this carbon. Methyl is on a wedge coming towards me, therefore it has to be up. This carbon, if I want something to go up on this carbon, it has to be on an equatorial position. So that's that. That's A. Now what about B and C? I'm going to do the same exact thing. Oh, sorry, the ethyl should be here, methyl should be here. My mistake. Yeah. There you go. So I'm going to do the exact thing. I'm going to choose this carbon, put it equatorial, and as a matter of fact, I'm going to choose this carbon again and make this equatorial. Since isopropyl on all 3 is on a wedge pointing upwards. So I've taken care of my bulkiest group, but what about the rest? So this carbon, if it's carrying the methyl group, this guy, methyl is on a dash now. Since this carbon is pointing downwards, or the vertex is pointing downwards, the only position I could have for going down should be axial. And this guy, since it's the same exact thing as my first compound, it will remain the same. And then here. Here my isopropyl remained on an equatorial, but the rest of my substituents, my methyl and my ethyl, are both pointing downwards. So if I'm choosing the same carbons, the down position will be given to axial. Since the only up position on these carbons can be equatorial, like I showed here. Any questions so far? Go ahead.
So where dash is always going to be an axial.
No. It could be equatorial or axial. Dash means going down. Okay? Dash means going down. Depending on your carbon, that could be axial or equatorial. Go ahead.
For the first one, which one is methyl?
Methyl is the one that has 1 carbon, this one.
Okay.
There you go. I erased it because it was incorrect.
Is for the third one,
Mhm.
is it better to have the isopropyl equatorial there, even though the other ones are axial?
Yes, good question. Because over here I have 3 hydrogens, and then I have 2 hydrogens here. So remember, this guy by itself is giving you 6 hydrogens just on one substituent alone. 6 hydrogens on one substituent alone, and actually there's going to be 1 here. So 7. Remember, I told you to prioritize putting your bulkiest group on equatorial position, even though you're going to have diaxial interaction. Yeah. Any other questions?
On the first one, does it matter which one is the ethyl and which one is the methyl?
So
Why did you switch them?
I remember, yeah, exactly. So I switched them because I'm looking at this from this direction. So for example, if I were to look at this, if I'm looking at it from this direction, my methyl is to the left and my ethyl is to the right. This way was the inverse. That's why I had to erase it. Okay?
Wait, why does it matter whether like the
So we're
groups are
using
axial or
axial if it also has a wedge. So I told you, wedge just means going up. So depending on the carbon it's on, it could be either equatorial or axial? Any other questions? Okay. So it says, based on the answer that we gave, which isomer is going to be the most stable and least stable? So in your opinion, between A, B, and C, which one's going to be the most stable? Well, why?
Because all of them.
Exactly. A is going to be the most stable because all of them, sorry, all of them are going to be equatorial. Which one's going to be the least stable? Yes, it has to be C. Because over here you only have one equatorial and you have two axials. This is what's referred to as my diaxial interaction. This is what's going to be causing your ring to bend. When that ring bends, that's when you start approaching your boat conformation. That's when your energy diagram starts to spike. We don't want to bend anything over here. We want everything to be spaced out properly. Okay? So C, because we have two axials and only one EQ. Go ahead.
Question. So like for the, is that a T-butyl or an isopropyl?
It's an isopropyl. If there was one more methyl attached to it, it would have been a T-butyl.
Okay, so for the, so like isopropyl has like the same, I guess, sort of properties as the T-butyl was there.
Yes. Yes. Yeah. Okay. Any other questions? All right. So part C. So we're given two isomers of 1,2-dechlorocyclohexane. So which one is cis? Which one is trans? That is correct. This should be cis. This should be trans. Remember, cis means both pointing in the same direction. Trans means both are pointing in opposing directions. Okay. So this could have been wedge dash or dash wedge. It doesn't matter. Or this could have been two dashes. What matters is having them in the same direction or opposite directions. Now the question is asking us, which isomer is going to be more polar? This guy or this guy? Which one do you think is going to be more polar? Or cis or trans? Any ideas? Exactly. Because think about it. Well, both of these guys are halogens, right? Both of them are going to be taking electron density away. So my dipole moment is directed towards these guys, right? So if I have two dipoles that are facing away from each other versus both of them pointing in the same direction, these guys are going to be taking it in the same exact direction versus two opposing chlorines. Therefore, what has to be more polar is cis compared to trans. Any questions? Okay. So after this page, we're just going to have one last page and we're almost done. We're almost there. Okay. So this question is giving us a line angle diagram of 3R, 4R, 4-T-butyl, 3-chloro, 3-methylpentane. This big guy right here. And it's telling us to draw the Newman projection of the most stable conformation. And C3 is my front carbon. So this carbon is my front. This is the back carbon. Remember, when I'm asking you to draw me a Newman projection, essentially your Newman projection is a two-carbon system, a front carbon and a back carbon. Everything else is treated as a substituent attached to those two carbons. Okay? So when I'm saying C3 is the front carbon, I'm saying I'm looking at this from this direction. So if this was my eye, for example, this is where I'm looking at. Now, pay attention. it hasn't given you any stereochemistry. It hasn't given you any wedges or dashes. That's because the question is asking you to draw the most stable conformation. It is asking you to assign wedge or dash to each of these depending on the stability. Okay? So in your Newman projections, go ahead.
How come 3 chiral if there's 2 methyl groups on?
3 methyl. Oh yeah, you're right. Let me take this off. You're right. Good catch. Yeah. But nevertheless, the question, I don't want it to be different. You have to draw the most stable conformation. Yeah, go ahead.
You can just fill it in based on the name. There's a,
3, if I want to change it, I mean, I designed it to be methyl. Let's see.
everything that has a 3 chloro and then 1 methyl.
Yeah, you're right. 3 chloro. Oh yeah, you're right. I don't. Yeah, you're right. There was an error in the print. So let me make this still 3R4. Okay. Okay. So when I'm trying to draw my Newman projections, remember, I have a 2-carbon system, a back carbon and a front carbon. But first things first, which one's going to be more stable? Is it going to be a staggered conformation or is it going to be an eclipsed conformation? Exactly. So whatever I have has to look like this. So they're not eclipsed to one another. Okay? So if I wanted to determine where to put these guys on the back carbon, I have 1, 2, 3 carbons, I have 4 carbons. Which one's going to be my bulkiest group on this carbon? Yeah, exactly. This is going to be the bulkiest group out of the bunch. And on this carbon, this is going to be the bulkiest group, my F. Since I only have 1 carbon here, and I have 2 carbons here. Okay? So, whatever I draw, whatever I end up having, I have to have T-butyl be facing anti to my bulkiest group. Okay? That's the first thing I'm going to do. So the first thing is determining should I do eclipse or should I do stagger. So between stagger and eclipse, I chose stagger. And when I do that, I want to determine which ones are going to be my bulkiest groups so I can face them away from each other as much as I can. This is going to be an anti-configuration. So I have them facing away from each other as much as possible. Okay? And then from here on forward, I can go ahead and determine chirality, so I would know where to put my chlorine and where I could put my methyl group. So here, we're saying this should be an R configuration. So if I'm saying this is R, that means whatever I'm counting has to be going this way. So let's determine the priority. So chlorine over here, since all of the rest of the atoms attached to this carbon number 3 are carbon, 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 this should be priority number 1. Okay? Now what about the rest of them? Here I have 2 carbons, here I have a big hydrocarbon chain. So this should be number 2. Now between an ethyl and a methyl, this should take a higher priority because this guy has 2 carbons, this guy has only 1 carbon. So I'm saying carbon 3 should be in an R configuration, so I want it to be going this way. But right now it's going this way. So what can I do to fix this? Remember, this is my lowest priority, my methyl group. Right now it's going counterclockwise. Right now it's S. What can I do to make it an opposite configuration? Exactly, exactly. If this was my least prioritized group, if it was facing towards me, then I would have to make it an opposite direction, basically. Remember, I told you, your least prioritized group should be facing away from you. But here, our highest priority is facing away from us. So whatever I determine, it has to be the opposite. So that's that. Now, what about the rest of my compound? So let's say this is my Newman projection as of now. If this is my front carbon or carbon number 3, let's say this was, if this was chlorine, this is what I should be having as of now. So I should have chlorine facing away from me, like this. It's going away from me if I'm looking at it. And I should have my methyl coming towards me, and my ethyl just be on a line angle diagram. So if I were to draw this right now, it would look like this. So that means my chlorine that was once facing away from me towards my page is now going to the right. So that would mean chlorine has to be on the right. Likewise, the methyl that was coming towards me and was on a wedge is now going to end up being to the left. So this is going to be CH3. So far, does it make sense? Yeah, exactly. The lowest priority group has to be the methyl group on carbon number 3. Yes. Okay. Now what about this carbon? So we said this has to be in an R configuration. Yeah, go ahead.
What if you didn't have a molecular kit?
Well, if you don't want to use this, then let's see. So if I were to have this guy with me, if you don't have a molecular kit, this is what I recommend doing. Instead, determine the chirality or the stereochemistry on the first carbon and use this as a point of reference to determine this one. For example, if wedge here ends up being on the left, if anything is on a wedge on this one, it has to be on the left as well. Yes. Okay? So I determined this is on the left, this is on the right. Now I'm saying my fourth carbon, or this one, has to be in an R configuration. So let's go ahead and design, assign configuration. So I have a little hydrogen here, don't forget that. I have a hydrogen there. So over here I have carbon, 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 hydrogen. I know this is going to be priority 4, but which one's going to have the highest priority? This one's the carbon attached to chlorine. The rest of them are all carbons attached to carbons. So this one should be number 1. The rest of my chain to the right. Now what about between T-butyl and my propyl? Since here I have 1, 2, 3, 4 carbons, here I only have 1, 2, 3 carbons, this should be 2, this should be 3. So right now I'm going 1, 2, 3, like this. So everything is looking good. So if this is looking good right now, that means that my least prioritized group should be facing away from me. So that would mean that my hydrogen should be on a dash. Okay? So remember, I'm saying my T-butyl should be facing away from my ethyl. So how can I make that happen? All I have to do, well, according to this kid, let's say, if this is my hydrogen facing away from me, and this is, well, let's turn. So I want T-butyl to be going up. So if this is going to be going up, that means hydrogen will be coming towards me. So according to this, hydrogen should be to the left. So that would mean that this guy is the one that has to be on a wedge. So this is C3, H7. Remember, I determined it based on my T-butyl. I said these two should be opposing to one another. And if they're opposing to one another, then hydrogen in this case will come towards me. Any questions so far? Go ahead.
So for this question, could you kind of look at it from the right perspective?
Right perspective as, do you mean right as in the direction right or the correct perspective?
Direction.
Okay, yes. I looked at it from this direction because the question is telling me, look at it with the C3 or carbon 3 being in the front carbon. This is carbon 3. I've marked 3 for you to indicate that's carbon 3. So yeah, I'm looking at this from this direction. Okay.
So if they had said that carbon 4 was the front carbon, would have been switched.
Exactly. Then I would have my Newman projection facing this way from me. Okay? Yeah, it all determines on your perception where it's telling you to look. Okay? For example, if something is on a wedge, depending on where you're looking at it, it could be left or right. Okay? Of course you're welcome. So somebody's asking us, how did you know that the Cl is facing away? So over here, we said that the stereochemistry on carbon 3 is R, right? And we determined the priority to be 1, 2, 3. So right now we're going from this direction. Right now it's going counterclockwise. Since we want it to be clockwise or going right, the only way I could do that is to have this guy facing away and my least prioritized group facing away from me. Because then I could make this inverse. Remember, in that nomenclature question I was telling you, if your lowest priority group is facing towards you, whatever you determine has to become the opposite. Any questions? Any questions? Go ahead.
I don't know if you already said this. So on the second carbon, why is C3H7 not on the left? Since it's in on a wedge.
Good. Because remember, if I were to draw just this, exactly what I have, tubular wouldn't be facing up, right? Tubular is facing down, actually.
Oh, okay.
So that's the problem. I rotated this in a way that put tubular up.
Okay.
I rotated it myself. Right now, it looks something like this. This is what I had originally. So this is what I have, for example. Okay? But I rotated the same thing. I didn't change them. I didn't change any of the substituents. If you do that, you're changing chirality. All I did was just rotate this. That's all. So now, these two, my bulkiest groups, are going to be anti to one another, something like this. That's why the white thing, the hydrogen, is now facing towards me if I were to draw it now. Okay? Make sense? Okay. Questions? Okay. So it says draw the corresponding Fischer projection now. Now remember, your Fischer projections, you remember they have a vertical line and you have a couple of horizontal lines here. Remember, your Fischer is basically asking you to put the rest of your hydrocarbon chain facing downwards and any of my substituents to be facing upwards. So in reality, my Fischer projection looks like this. These two are on a dash, the rest are going to be on wedges. So my Fischer, for example, looks like this. These two facing towards me. Does it make sense? So my substituents are coming towards me, while the rest of my hydrocarbon chains are going away from me. They're on a dash. Okay? Now over here, the rest of my hydrocarbon chain on this carbon is going to be actually this guy. Since it has 1, 2, 3 carbons, well, this guy only has 2. Therefore, I know C3H7 should be facing away from me. You can do it either way. You could put C3H7 here or here. It doesn't matter. Okay? And that would mean that 1, 2, my ethyl here, my C2H5, should be over there. So with that in mind, if I wanted to convert my line angle to a Fischer projection, what would it look like? So you can use the chirality that you've been given already. For example, if I put the chlorine here and my methyl here, what would be the chirality of this carbon? This is 1, like we determined. I'm just using this. This is the template I have already. Okay? So chlorine is 1, and then I said the rest of my chain is going to be 2, and then I said my methyl is going to be 4, and this guy is going to be 3. So I would have this right now, right? So this is S, but since my least prioritized group is facing towards me, that would mean that this is actually R. Remember, whenever this happens, least prioritized group is facing towards me, I have to make it the opposite. Go ahead, ask the question.
Why is the C2H5 not on top? It's connected to the...
You could do it either way. It's okay. You could do C2H5 on top.
But with it connected to the chlorine, would the C2H5 not be connected to the chlorine?
Oh, you're right. My mistake. Yeah, good catch. I apologize. Good catch. I apologize. Yeah, you're right. You're absolutely right. Yeah. you're correct. So let's determine chirality on this one then. So if I had chlorine here, and if I had CH3 here, okay, thank you for that. So C2H5 is here, chlorine here, chlorine. Okay, so this was number 1. Again, rest of my chain is 2, this guy is going to be priority 4, this guy is going to be priority 3. So right now I'm looking at 1, 2, 3. I'm going this way. So right now it's S. But since the least prioritized group is coming towards me, I can make this the opposite. So in reality, this is actually R. So I'm obeying the rule that is given to me. Okay? So this is correct. This is good so far. But what about the second carbon? So I have C3, H7. Now what about the chirality here? So we determined that the rest of our chain should actually be number 1. And then we determined our T-butyl is number 2, and our propyl is going to be number 3. So remember, I'm trying to make this guy be R as well. If I want this to be R, I have to structure it in a way that is S actually, since everything's coming towards me. So since this is 1, this is 3, all I have to do is just put the second priority over here, which would be my T-butyl. That will mean the hydrogen is here, which is my 4th priority. So right now I have 1, 2, 3. Right now it's S. But since everything is coming towards me, including the opposite, the least prioritized group, I have to make it opposite. So this will be the resulting Fischer projection that I would have. Let me make it a little more neat. So this will be a C2H5. You could do CH3 as well if you want for T-butyl. You don't have to just draw the forks. Okay. Any questions on Fischer projections, Newman projection questions that we did?
If it were completely flipped upside down, that's also.
If you rotate the same exact thing 180 degrees, it's fine. So you're saying if, for example, C2H5 was on top and C3H7 was on the bottom, that will still be fine. As long as you're obeying the chirality, as long as they're both R. Okay. Questions? Okay. So last question on this page. Question 8 is asking us to identify chiral carbons and indicate whether they're R or S. So before we approach this question, let's go over the definition. So I'm saying something is chiral when it's attached to 4 substituents, and all 4 of those substituents are different. So for example, if I have a carbon that's attached to 2 methyls or 2 hydrogens, they're not going to be chiral. Or if I have a carbon that has, for example, a double bond and has 3 substituents, it's not going to be chiral. Now with that in mind, let's go ahead and take a look at our question. So over here, these carbons are all the same, right? They're carbons of the same ring, basically, a benzene ring. Now this carbon has 1 hydrogen attached to it, a double bond, and another single bond. That will mean this carbon has 3 things attached to it, therefore this isn't chiral. We need 4 things and all 4 being different. Same with this carbon, 1 hydrogen, 1 double bond, 1 single bond. Not it. Same with this one, not it. Not chiral, not chiral, not chiral. Remember, so you're noticing a trend. Any of the carbons that were double bonded, I immediately kicked them out. Okay? Because none of them have 4 things. Now what about this guy? This guy's double bonded, so it doesn't count. This guy's double bonded, it doesn't count. Double bonded, no. Double bonded, no. So just by knowing this one little factor, I eliminated the entire molecule from this segment. So I'm just looking at this point. Okay? So over here, this carbon, it has two hydrogens, right? Since it has two of the same things, it cannot be chiral. So this guy's not. Now, since we're absorbing carbons, let's see. So over here, I'm going to have a hydrogen on the dash. So let's see. I have a methyl group, I have a hydrogen, I have a nitrogen, and a double bonded carbon. So 4 different things. So this guy should be chiral. So that's step number 1. So this is going to be my chiral carbon. 1 methyl, 1 hydrogen, 1 double bonded carbon, and 1 nitrogen. 4 things, all 4 different. So how do I go about determining RMS? Well, just like we've been doing. Let's determine priorities. Here I have carbon, carbon, hydrogen, nitrogen. So nitrogen should be priority 1, hydrogen should be priority 4. And between my single bonded carbon and double bonded carbon, whenever you see double bonds and triple bonds, think of them like this. For example, if I have a carbon that's triple bonded to another carbon, that would mean this carbon has 3 carbons attached to it, like this. Okay? So that would mean this carbon has 3 hydrogens. This carbon has 2 carbons and another carbon, basically. So this guy has 1 hydrogen, 2 carbons. So my double bonded carbon will be higher in priority. So if this is 1 and this is 4, this guy should be 2. So methyl will be 3. So I'm looking at 1, 2, 3, 4 in this direction. So right now I'm doing this way. So therefore this should be R. Any questions? Okay. Now what about this one? Let's do the same thing we've been doing so far. Let's eliminate all the double bonds and all the triple bonds so I don't have to look at them all the time. So for example here, I have 3 hydrogens attached to this carbon. So this can't be the chiral carbon. This carbon is triple bonded, so it's only attached to 2 things that won't count. Same with this carbon, triple bonded, won't count. Now what about this carbon? So I have carbon-nitrogen triple bond, 1 thing. Carbon-carbon triple bond, 2 things. A carbon-carbon double bond, 3 things. And a hydrogen on a dash. So I have 4 different things, therefore this center should be chiral. Now let's see. Remember this CM, this is the same C triple bond nitrogen that we've been talking about. So here, we know hydrogen is going to be 4, so that's that. Here I have carbon, triple bonded to nitrogen, carbon, 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 carbon. So this should be number 1 because it's attached to a nitrogen. Now here, between a triple bond and a double bond, this would mean that I have the carbon attached to 2 carbons. This way I have a carbon attached to 3 carbons. So this should take priority. So this should be number 2, this should be number 3. So what I'm dealing with right now on my second compound is 1, 4, 2, 3. So I'm going this way. So since I'm going clockwise, this should be R as well. What about the rest of them? This guy's double bonded, doesn't count. You might get tricked and see, well, this guy has a wedge and a dash. It's indicating stereochemistry, then this might be chiral. Here's the thing, you have 2 methyl groups on the same carbon. That won't count as chiral. So this guy won't be chiral, this guy won't be chiral. And this guy has 2 hydrogens attached to it, this won't be chiral. And the same for these 2. These guys are double bonded, they are only attached to 3 things. So they're going to be achiral. But what about this? I have a hydrogen on a wedge. Let's go ahead and determine if this is chiral. So I have alcohol, or OH, sulfur, double bonded carbon, and hydrogen. So 4 different things. So if I have 4 different things attached to this guy, and all 4 of them are different, this should be chiral. So which one is highest priority? Between sulfur and oxygen, this guy is heavier, so this should be number 1. Then this should be number 2. And hydrogen is always, 1, 2. This is always going to be number 4. And that would mean this is number 3. So right now I have something that looks like this. 1, 2, 4, 3. Now here's the problem. If I go 1, 2, 3 like this will be R. But the problem is, since my hydrogen is coming towards me and I want it to be facing away from me, my stereochemistry should be inverse. So this R would actually be an S. So on this compound, I had 2 chiral centers. Go ahead.
Or the carbon next to the triple bond, the double bonds.
Which
Or
one?
with the chiral center?
Yeah.
That one?
Uh-huh.
Why is so the triple bond, it has higher priority than the double bond?
Yes.
But that other carbon that it bonds to just on the cyclohexane,
Mm-hmm.
wouldn't that carbon have 3 carbon bonds? Or
See, we're looking at it in terms of order, let's say. The first thing that's attached to it, if they're the same, then the next thing that's attached to it. If that's the same, then the next thing that's attached to it. Since both of them are attached to carbons, for example, here, so here I have carbon attached to carbon, carbon attached to carbon. However, this is triple bonded carbon, this is double bonded carbon.
there's another carbon that's attached to this one, right?
Yeah, and this is another carbon that's attached to it as well.
But it doesn't have 2 carbons.
Yeah, I get it. But the thing is, over here, this guy already wins in terms of determining priority because it has a triple bond. This guy already wins. That's what I'm trying to tell you. And besides this triple bond, remember I told you, having a triple bond is like saying I have 3 carbons surrounding me versus just 2.
Yeah, but doesn't it have a double bond? It's like saying 2 carbons and another carbon. So it would make 3.
He's saying it is the single bond below it as well, with the double bond above it.
This?
Yeah.
Uh-huh. Yeah, but still, I'm saying, since this guy is double bonded, this guy's triple bonded, this guy already gets the priority because it has a triple bond. I know what you're asking. You're asking, well, this guy, it all adds up to 3 bonds. Well, sure, that adds up to 3 bonds, but this guy is a triple bond, basically. This is one thing. Those are 2 different things. Okay?
Also, if you go to the next carbon, the other one has 4 carbons, and then the next one has 3.
Okay. Any questions on this one? Go ahead.
So what does the CN
Mm-hmm.
imply the high energy?
No, I drew CN for you. So CN looks like this. I already drew it here. Yeah. Yeah, sure. Questions? Okay. So what about this one? Remember, if I'm not indicating anything here, I'm assuming these are methyl groups. So, let's see. So there are 3 hydrogens here, 3 hydrogens here, and 3 hydrogens here. Okay. So let's go ahead and determine chirality. So over here, I have 1 carbon, a back carbon, and then my methyl group at the very end. But is this chiral, for example? Is this carbon chiral? Let's see. I have 1 hydrogen, but 2 methyl groups attached to it. Since these 2 are the same thing, they can't be chiral. And the methyls themselves, they can't be chiral because they have 3 of the same things, hydrogens. Same with this methyl. This has 3 hydrogens. But what about my back carbon? Well, here's the thing. I have chlorine, I have methyl, I have hydrogen, and I have the rest of my chain. Since those are 4 things, and all 4 of them are different, the back carbon, this big circle, this should be chiral. Now let's see. I have chlorine, carbon, carbon, hydrogen. So chlorine should be number 1, hydrogen should be number 4. Now between methyl and the rest of my chain, the rest of my chain would take priority compared to a methyl because I have a carbon that's attached to 2 other methyls, whereas I have a carbon that's attached to 3 hydrogens. So the rest of my chain, or this guy, should be number 2, this guy should be number 3. So if I were to indicate it on, let's say, a Newman projection, let's say I have this, right? So I have this being the rest of my chain, this being my hydrogen, the red one, the chlorine, with the green one being the methyl group. So I'm saying this is 1, this is 3, this is 2. So I want to determine it with hydrogen being the least prioritized group facing away from me. So in this way, I would have 1, 2, 3. So I'm going to the counterclockwise direction, so this should be an S carbon. Go ahead.
For this, if you eclipse the Newman projection, you need a Fischer projection to determine it without it.
You can make this a Fischer projection if you want. You can do anything with it as long as you don't switch your substituents around. Yeah. You can make it line angle, you can make it Fischer, you can just do Newman projection, whatever is up to you. Whatever you like. Okay? And last one. So here we're giving a Fischer projection. That means that these two are on a wedge, and the same with these two, and these guys are on a dash. So let's go ahead and take a look. This carbon can't be chiral because it's attached to 3 hydrogens. This guy can't be chiral because it's attached to 2 hydrogens. What about this carbon? So you might say, well, this is attached to 2 carbons, this is attached to C2H5, COH, and the rest of my chain. These are 4 different things. Here's the thing. If I draw out C2H5, it will look something like this. Since I have, well, this is my R chain. Since I have 2 of the same things attached to the same carbon, I have 2 ethyl groups attached to the same carbon, this can't be chiral. I want 4 different things. But what about this carbon? So let's take a look. So iodine takes the highest priority here, because here we have carbon, carbon, nitrogen. And then nitrogen will take the highest priority here. And then between our carbon, our ethyl group, and the rest of my chain, this should take priority because it's attached to a carboxylic acid. Here we only have 2 carbons with 5 hydrogens. So this should be 1, this should be 2, this should be 3, and this should be 4. Now here's the good thing. I don't have to inverse anything because the least prioritized group here, number 4, is already on a dash. So whatever I determine is going to stay what it is. So let's see, I have 1, 2, 3. So like this. So since I'm moving clockwise, this guy should be R. Sorry. Any questions? Go ahead.
Can you explain why the bottom carbon is not chiral?
Of course. So I gave this question to you on purpose. I made C2H5 on purpose. C2H5 is an ethyl, right? Well, here's the thing. This guy is an ethyl too. So this carbon is attached to 2 ethyls. We want 4 things out of 4 different. Since these 2 are the same, it can't be chiral. Okay. Sure. Questions? Questions? Go ahead.
So, Newman projection, why is it S instead of R? Because when you convert it to a Fischer projection, you have to flip it. I mean, that's not a good thing.
So if you want to do a Fischer projection, you can. There's nothing against it. So here, my Fischer projection, let's say I have this right now. Let's say I have this. My Newman projection is this, right? This is my hydrogen. This is my chlorine. This is my methyl. Just like my back carbon. Right? So if I wanted to make this a Fischer projection, I would have to rotate this in a way that the rest of my hydrocarbon chain is facing downwards and all the other substituents facing upwards. So for example here, my methyl is the rest of my hydrocarbon chain, the green guy. So if I rotate this in a way, this is what I would have. So I would end up with this. So I would have, for example, CH3, CH3. So what happened? Thank you. So I would have CH3, CH3. And then here I said the red guy is going to be chlorine. This is going to be CH3. And then I would have, what else? Actually, this should be hydrogen, since I want the rest of my hydrocarbon chain to be this way. So let's say this is going to be hydrogen. So now you can determine the chirality of what you have. So this should be number 4, this should be number 1, this should be number 2, this should be number 3. So if I do this, I get 1, 2, 3. Right now it's S. But since hydrogen, my least prioritized group, is coming towards me, right now it's like this. Sorry. So right now we're going 1, 2, 3. So we're going this way. We're going R, right? But because hydrogen is coming towards me, I have to make it the opposite, basically. That's why my R will become an S. Okay? If you want to do Fischer projection, you're fine. If you want to do line angle, you're also fine. Either one is all up to you, whichever one helps you. Okay? Any more questions? Okay. So you guys made it. Last question. So last question, we basically have a couple of compounds. For all of these, we have to determine the relationship between these two compounds. These two, and these two. Either they are identical, enantiomers, diastereomers, constitutional isomers, resonance, but they're not related at all. So let's go ahead and see what we have. So for this one, let's see, I have one iodine, one NO2, one phenyl, one hydrogen, one carbon. I have the same exact things here. So they can't not be related. They have the same molecular formula. So they have to relate in some way. Since I'm giving stereochemistry, why not go ahead and just determine what I will have? So for example, this way. Let's say this is what I have right now, and hydrogen is my least prioritized group, as you can see. So this should be number 4. Phenyl is just benzene. So this is basically carbon. So iodine should be number 1. Nitrogen should be number 2. And this guy should be number 3. So this is what I have as of now. But if I determine the chirality looking at it like this, I will have to inverse it. So you can determine it like this and inverse it, or just flip it around like this. But if I do it like this, I would have 1, 2, 3. So I will be having an S. But since hydrogen is coming towards me, I have to make this R. Now what about this guy? The priority is still the same. This is 1, this is 2, this is 4, and this is 3. However, now I would have my least prioritized group here. If I wanted to determine the chirality, I would have to have it facing away from me. So like this, I would have 1, 2, 3. This is basically what I'm converting. So 1, 2, 3. This will also be R. So they have the same exact stereochemistry, the same exact molecular formula. Therefore, they should be identical to one another. Go ahead. Yeah. What's the problem?
Don't you have to rotate the molecule if your small substitution is not on a lighter dash?
So I did rotate it actually. So this is what I had initially, right? This is what I'm looking at.
Yeah.
So I rotated like this. This is how I determined the stereochemistry.
Do you mind drawing it out for writing it down?
Writing it. Oh, okay, sure. So it would look like a Newman projection. So if this is what I have right now, and if I'm looking at it from this direction, I would have this. So I would have phenyl up top, iodine to my right, NO2, and hydrogen will be this back thing, basically. This is hydrogen. So think about it. So this is what I have right now, right? Okay. So I want this guy to be facing away from me. Since this is NO2, NO2 now is to my left. Phenyl is now to the top, just like it was here. And iodine, which was here, is now to the right. Okay? So now you can go ahead and determine the chirality. So 1, 2, 3. I'm going to the R direction, to the right. So this should be R as well. Since I have two compounds that have the same molecular formula and the same stereochemistry, they should be identical to one another.
Why would we flip it though? Because hydrogen is normally if hydrogen is into the page.
You can determine this already with the perception that you have. I'm just doing it so it's easier for you guys a little bit. I'm just rotating it so hydrogen is facing away for you guys, like this. Sorry, like this. Hydrogen is this guy. You can determine chirality based on any perception you have. You can just determine this by looking at it right now. I'm using this guy to make it easier for you guys a little bit. That's all. Okay. So, any questions on this guy? Okay. So, what about this? So, I have 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. 1 nitrogen. 1 nitrogen. And then let's see. So, I have 3, 6, 8, and 1 here, 9, these two, 10, so 10 hydrogens, and here I have 2, 4, wait, let's see, so I have 2 hydrogens here, so I would have 3, 9, and this would be hydrogens. So since I have the same exact molecular formula between these two guys, however, the only thing that is different between them is me having moved this methyl group to this location. So whenever I get this, whenever I have the same molecular formula but different bond arrangement, this is what I would have something called constitutional isomers, just like T-butyl and let's say isobutyl. Remember, I was moving a methyl group around. So since I have the same molecular formula but different bond arrangement, this should be a constitutional isomer for me.
There's some noise in chat about the second one being an S.
Which one? Oh, the first compound we determined? Okay. So here's the thing. So this is 1, this is 2, and this is 3. Let's say, so this is what I have right now, right? So if the white bulb is hydrogen, this guy is NO2, and this guy is I, right? I want this guy to be facing away from me when I determine my chirality. So I'll just do this, right? So when I have 1, 2, 3, when I'm going this way, this should be R. It can't be S. Remember, this is what I have right now. This is the equivalence of this. Okay. Any questions on either one of the first ones or the second one? Yes?
Is that because the hydrogen isn't dashed? Or is it just on plain paper? Is that the problem?
For which one? The first one or the second one? First one. So I want hydrogen to be facing away from me when always and always. When I'm determining chirality, I want the least prioritized group to be facing away from me. Okay?
Is the rule that if hydrogen isn't facing away from you, then you just flip it?
Flip it, you're gonna have to show me.
As in, it's S. As in, we see if it's S. And then, so on there, I mean, it looks like R, because it's 1, 2, 3
Yeah.
on the page. And then, but because hydrogen isn't looking away from us, then we flip it.
Well, I just showed you on the Newman projection. So for example, this is what I have, right? So this hydrogen, this is what I have at the moment. This guy's facing away from me. This guy's on the plane of the paper, basically, like this. So since I have this, if I want hydrogen to be facing away from me, I can just do this. So this will be 1, again, my iodine, 2, 3. So this should be an R configuration. Okay.
So there is no, so you can't do that, as in you can't determine whether, just on the Fischer diagrams, you did that.
Yeah, you can determine your chirality. I can, well, not use this and determine chirality on this one. But then that would depend on how I'm looking at it. For example, if I were to look at this and determine, I would look at it as if this hydrogen is coming towards me. Whatever I determine, I'm going to inverse it. You could not use this. Yeah, it's always your choice. You just have to have the correct perception. And the correct perception is hydrogen facing away from you. That's what I'm trying to emphasize. If you stay afterwards, I can show it to you, okay? So what about these guys? Now, if I were to take these two and make it 2D, what would they look like? So here, this is equatorial going down, this is axial going down. Both of them are facing away from me. So I have two ethyl groups, both facing away from me. Now what about this guy? Here I have this one equatorial down. Here I have equatorial going up. So these two, they have the same molecular formula. Same cyclohexane, two ethyl groups. The problem is, if I were to determine R and S, it will be the same for these two, but not the same for these two. So I can't say they're identical because we have a chirality difference. And I can't say they're mirror images of one another. Therefore, if they're not related, if they're not resonating, since I have no double bonds, no charge, nothing, everything is sp3, I'm stuck between these three. Since I haven't even changed or touched any of my bond orders, the ethyls are still where they are, so it can't be constitutional either. So I'm essentially determined between these three. So because I have a chirality difference, they're not identical. And because I can't say these two are mirror images of one another, it has to be diastereomers. Constitutional is when I start changing my bond orders. For example, let's say if I took this ethyl group right here and I put it on this carbon. Okay? When I have bond arrangement differences, that's when I have constitutional. These two are on the same exact carbons. The only point of difference is chirality. Okay? Go ahead.
Are cis-trans isomers always going to be diastereomers?
Yes, they are. Yes, they are. Cis-trans are always going to be diastereomers. Questions? Okay. So we're looking at this guy and we're looking at this guy. So we have one oxygen here, and we have 1, 2, 3, 4, 5 carbons in the same ones. At first glance, you might say the resonance structures of each other. But if I were to resonate them, for this guy, I could have this guy giving the electron to my carbon that has a positive charge, forming a double bond here, and moving my positive charge here. And here, my resonance structure will be my double bond has to stay here because everything else adjacent to it is sp3. This is sp3, this is sp3. So what about my oxygen? I can't take this electron and just give it to oxygen, so oxygen becomes neutralized, but my positive charge will end up being here. So do these two have any relation to one another, either resonance structures of each other? No. Because here, my carbocation is over here, my sp2 hybridized carbon is here, here my sp2 hybridized carbon is here. These two are sp2, these two are sp2, but the difference is between these two carbons. Since they're not resonance structures of each other, then they can't even be related to begin with. I haven't moved any bonds around. I haven't, for example, assembled a different carbon here or an oxygen with a hydrogen there, so I can't say they're constitutional. And since I just proved that these two are not the same, they can't be identical. And since I have no chirality points, I wouldn't be able to do enantiomer or diastereomer. So they should be unrelated to one another. These are two different structures. Questions?
Do they not have the same molecular formula?
Yes, but still, I'm saying, wait, let's see. So for example, here I would have 2 hydrogens. Here I would have 1, here I would have 1, 1, 2, 2. Okay, so I have 2, 4, 6, 7 hydrogens. Here I would have 2, 1, yeah, okay. So I have 2, 4, 6, 7. You're right. I missed this question. You're absolutely right. I'm going to change this question for you guys. Yeah, I'm going to leave this guy out. Good catch. Yeah, I'm going to leave this guy out. Okay. So what about Fischer projections? Newman, this guy. So for my Fischer projection, I'm just going to go ahead and do this so you guys know that I'm dealing with wedge on my substituents and then dash on the rest of my chains. So here I have T-butyl, T-butyl, ethyl, ethyl, 2 hydrogens on my substituents, 1 bromine, 1 methyl, and 2 carbons. So they have the same molecular formula. They have the same things in it. But there is a difference between them. If I were to compare these two, the first thing I would want to do is find a point of comparison. For example, here, C2H5 is facing downwards. Here, C2H5 is facing upwards. So what I would like to do is actually do a 180. So I'm going to make everything the opposite. So if something that's going right and up will be left and down. Something that's going left and down will be right and up, for example. So for example, I could do this. So since this is down, this will be up. Since this is up, this will be down. This is left and down, it will be right and up. Remember, everything is becoming an opposite since I'm doing a 180-degree difference. This is left and up, it will be right and down. This is right and up, it will be left and down. And here we will have left and up. Now we can compare these two to one another. So this part is the same between them. However, this segment is indicating that I have a chirality difference between them. So if this guy is chiral, they will have the same chirality. Everything is arranged the same way. But these two are different. So it's looking like the same situation that we had here. These two were the same, but these two had different chiralities. So since I can't say they're identical, and since I can't say they're enantiomers, all I'm left with is to basically say they're diastereomers. That one point of chirality difference that prevents me from saying they're identical or they're enantiomers. Questions? Go ahead.
They're not enantiomers because they're not mirroring.
Exactly, exactly. Think of it like this. If both those chiral centers were the exact opposite of this two, then they will be exact, they will be mirror images of one another, like a left hand and right hand. Yeah. Questions? Okay. So here, let's see. I have one carbon that's attached to a methyl carboxylic acid chlorine, carbon that's attached to methyl carboxylic acid chlorine, and my back carbon that's attached to two hydrogens, and one methyl. So my molecular formula so far is the same. So I can't say they're not related. So let's go ahead and determine the chirality of each one, and if they are chiral to begin with. For example, here on my back carbon, I have one methyl but two hydrogens. Since I have two hydrogens, this can't be a chiral center. So this guy is off. What about my front carbon? I have a methyl, a chlorine, a COOH, a carboxylic acid, and the rest of my chain. So this guy is chiral. But what about the chirality? So let's go back to our model kit. Let's say I have this guy right here. So if I had, let's say, something that looked like this. If I had my carboxylic acid on top, my chlorine over here, and my methyl group here, and what's facing the back of me is going to be my chain. So if I wanted to determine the chirality, my carboxylic acid, this guy is carbon, carbon, back carbon is still carbon, chlorine should be number 1. So I'm going to indicate the chlorine with this silver ball. So like this. So this is number 1. And then between carbon attached to oxygen and carbon attached to carbon, this should be number 2. And my methyl should be number 4. And the back carbon should be number 3. Because back carbon is attached to another methyl. This guy is just a methyl alone. So right now, I have my lowest prioritized group that's facing towards me. So what I can do instead is try to rotate this around in a way that it's facing away from me. So this way I would have 1, 2, 3, this being an R configuration. And again, since they're the same atoms, they're going to have the same prior. This should be 1, this should be 2, this should be 4, sorry. And the back carbon should be 3. So again, right now I'm dealing with this. I would have my methyl group coming towards me. Yeah. Chlorine going towards me, carboxyl coming towards me, but methyl also going towards me. So what I can do is rotate this around like this. So I would have 1, and I would have 2 and 3. So here now I have 1, 2, 3. So now I'm going counterclockwise. Since this guy is S and this guy is R, they're the exact opposites of one another. Here's when I can say I actually have an enantiomer, because the chiralities are the exact opposite of one another. One is R, the other is S. Any questions? And the last one. So on this question, I want you to remember, whenever you see a compound like this, don't think of it like an arrow that's pointing upwards. Think of it as a bent paper, like this, for example. Something that looks like this. A bent paper. Okay? So, let's see. My molecular formula is going to be the same because I have 1 oxygen in all of them, 1 phenyl. My bridge carbons are going to be 2, and the rest of my chain, my cyclohexane, my cyclic compound is going to have the same number of carbons. So if I were to take these two and put them in front of each other, let's say they had a line of comparison here. What I would actually end up having is these two being mirror images of one another. Let's say if I wanted to rotate this around. If I did a 180, my oxygen would be on the left and my phenyl would be coming towards me. Just like how I could have a right hand and a left hand. Of course. This. Is that better? Okay. So we're saying, what would the chiralities look like on diastereomers? Good question. So in your diastereomers, your chiralities are going to be different, but in a way that prevents you from saying they're mirror images. So for example, you have the 1 point or 2 points of chirality difference that prevents you from saying they're identical or they're enantiomers. When you can't say they're enantiomers or identical, you're only left with diastereomers, basically. Okay? So I'm saying if I were to move this around, if I were to switch this around, my oxygen would end up being here, and my phenyl would end up being forward. So since these two will be the exact opposites, if I were to place them with one another, if, for example, my thumb were to represent the oxygen, these two will be exact mirror images of one another if I were to place these two in front of each other. Since you have no bond movement, basically, and you don't have any sp2 hybridized things to say they're not related, sorry, they're resonance structures. They can't be constitutional or resonance, and they can't not be related since they have the same molecular formula. So all I'm left with is these three, basically. And since I told you, if you were to take these guys out of the page and compare them to one another, they would end up being mirror images of one another. Let's see. I think that's it. If you have any questions about the problem set, if you have any questions out of the problem set, please feel free to ask me. Yeah. Yeah.
The last page is can you ignore that fourth question?
Sorry, I couldn't hear you.
What do you think about that severe weather?
Man, what did I need to text message?
Stop rating.
Yeah, like when I say small.
Okay, let's be clear on this one, so. Hopefully it's. Well, unfortunately, not everyone has a cover umbrella.
Yeah, nothing, probably like nothing here matches. Yeah, here's just it's just. But I heard it once.